Hello and a very warm welcome to everyone joining us for today's Select Science webinar titled Development of a HPTLC Method for Evaluating Vegetable Oil Adulteration. My name is Carrie Haslam and I'll be moderating today's presentation. Today I'm delighted to be joined by Dr. Tian Du, Chief Scientific Officer at CAMAG, and Paul Roboz, Junior Research Assistant at Nestlé Research, as they discuss how a newly developed HPTLC method was developed to identify edible oils, plus find out how it was used to detect adulteration with remarkable accuracy. Please feel free to submit any questions you may have during the webinar today. To do this, simply head to the engagement window to the right of the auditorium and click to open the Q&A window. So without further delay, I'm delighted to hand over to our speakers and would like to thank them for presenting with us today. Please go ahead.
So thank you for the introduction. So as it was mentioned before, today we will talk about the development and applicability of an HPTLC method for evaluating vegetable oils adulteration. So we will start with some definition on vegetable oils. Then I will show how we develop the method and how we transfer this method to the industry. Then Paul will talk about the applicability and will conclude. So the Vegetable Oils Project was initiated by the USP, so the United States Pharmacopoeia, with their General Chapter 202 on fixed oil. So the method was published in 2015, and since then it was working quite properly, apart that the production of plate was different and the availability of the plate was really limited. So we had to revise the method to be now more reproducible. So the method from the USP is called the fixed oil method for the chapter 202 and was used initially for 15 oils. So you have here the example. We had the olive, the corn, the almond, the canola, the cottonseed, the evening primrose, the flaxseed, palm, peanut, sesame, soybean, chia, safflower, borage, and sunflower oils. So you see that on the fingerprint that they have all different fingerprints. So the method was good to differentiate them. Inside the method, in the HPTLC method, so each oil were dissolved in 3 milliliters of dichloromethane. The USP reference was prepared the same way as the sample. And for the SST, they used the corn oil and the olive oils as SST. The plate used was the HPTLC plate RP18 from Merck with an indicator of fluorescence or not, depending on what you have. Then the plate were pre-washed before with dichloromethane, then dried in the oven at 120 degrees for 10 minutes. The mobile phase used was dichloromethane, acetic acid, acetone with the proportion 2:4:5, developed with a developing distance of 80 millimeters, a saturation time of 20 minutes, and an activation at 33% of humidity. The method used a derivatization step using phospholipid acid, and the detection mode was the white light after derivatization. For the new fixed oil method, we have decided to extend the method to 20 fixed oil. So you have the 15 that were initially in the current method, but now you have more the castor oil, the hydrogenated castor oil, the koic seed oil, the krill oil, and the black cumin seed oil. To develop the method, we had some optimization to do. The first optimization was the mobile phase. So the mobile phase has to be reproducible, and we wanted also to have only one method for the identification of each oil. What we wanted to do also was to be able to detect some adulteration. So this was the additional test that we had to do. So for that, we had different steps. So the first step, we wanted to replace the derivatization step to make it easier during the method development. Initially, the method is done with phospholipid acid, and this reagent you need to heat your plate at 120 degrees. So it's quite high. So we wanted to have something different. And we did a comparison with the anisaldehyde sulfuric acid reagent. So you see here the result. On the left side, you have the sunflower, the corn, the cottonseed, and the safflower oil derivatized with phosphomolybdic acid. And on the right side, you have the same oils derivatized with anisaldehyde sulfuric acid. So you see that here we have no significant difference between both reagents. We are detecting the same sequence of zone. So we could replace actually the phosphomolybdic acid by the anisaldehyde. So that's why we use then the anisaldehyde for the rest of the test. For the second part, we optimize the developing solvent. So in the current method, it's using acetic acid acetone dichloromethane. We did several tests to optimize the method, and taking into account that we wanted to have some green solvent also, then we came with a new developing solvent using acetonitril and cyclopentyl methyl ether, 7:3 as ratio. So cyclopentyl methyl ether, we call it CPME. It's a green solvent. So you see now the result on the right side. So with the initial developing solvent, all the fingerprints are really in the middle, in the center of the chromatogram. With the new developing solvent, the fingerprints are covering more of the HPTLC fingerprint, the chromatogram, and we have a better separation of each zone. So with the separation of each zone, then we are able to distinguish more each oil. So here, for example, we have a better fingerprint for the safflower oil in the new developing solvent compared to the left side where we have less zone in the upper part. To be sure about this, the reproducibility of the developing solvent, what we have done is test this solvent on different batch of plates. We have here some results. So you have two different batches, and you see that the same oil give you exactly the same fingerprint in the other batches. So the method is reproducible batch to batch, which was quite complicated with the current method. For the third step, we wanted to optimize the sample preparation. Initially, the USP method for the sample preparation is using dichloromethane. We wanted to compare the dichloromethane with the CPME and also a mixture of CPME methanol. When you look at the result on the right side, so you have on the left side, you have the CPME methanol mixture. In the center, you have the dichloromethane, and on the right side, you have the CPME. So you see that here, there is no significant difference between the solvent that is used for the extraction. So in that case, we wanted to keep the CPME to have the same solvent in the extraction than in the developing solvent. Then after that, we have optimized the application volume. For the application volume, we wanted to check 4 and 8 microliters. So you have here an example with the cottonseed oil, corn oil, olive oil, palm oil, sunflower, almond, and borage oil. We have applied 4 and 8 microliter all the time. And you see that here, what we wanted is to see more zone. So it's what we see with the 8 microliters here. All the time we see more zone, but we have also to be sure that we are not overloading the fingerprint. So with 8 here, we see that we are seeing more zone, but it's not overloaded. So that's why we keep the 8 microliters. For the step number 5, we optimize then the derivatization step. I told you for the method development, we wanted to use something simpler than the phosphomolybdic acid. So we have used the anisaldehyde sulfuric acid reagent, but we didn't really test it other derivatization reagents. So here is what we have done. We have tested the anis sulfuric acid reagent and compared it to the sulfuric acid reagent in methanol. And we have also another recipe for the anisaldehyde sulfuric acid, so what we call the modified AS. So the results are on the right side, and you see that here the first derivatization with anisaldehyde, it's working, it's good. 10% sulfuric acid in methanol, it's also giving us the same kind of result, just that in white light, the zones are more orange than purple, so which is not the best if you want to really describe the fingerprint. Then if you compare with the modified anisaldehyde sulfuric reagent, here we have more information. You see that in white light, we start to have different color. Everything is not just violet, purple. We start to have some pink zone also. So this can help when you want to discriminate, or if you have some mixture, the purple zone will make the difference. So that's why at the end, we went for the anisaldehyde sulfuric acid modified. For the step number 6, we wanted to select the system suitability test. So the system suitability test is a control standard that we use to make sure that everything went well during the chromatography. Initially, in the USP method, they use the corn oil and the olive oil extract. So here, the problem is that when you use an extract, there is also some natural variability that you have to take into account. So that's why here we wanted to have another proposal and use some reference standard. So we propose a mixture of triolein, oleic acid, and the 1,3-diolein. So you see here on the tracks 1, 4, and 7. So when we compare the fingerprint, we see that the mixture that we propose cover the chromatogram, or at least the zone of interest, so which is good if you want to see if the chromatography went well in this area. So that's why we have decided to go for this mixture, triolein, oleic acid, and the 1,3-diolein. We have then tested this proposal of SST on 11 plates from 2 different batches done on 3 different days by 4 different analysts using 4 different ADC tools. So we compare all the data from the SST, and we see that here on all the results, we have a standard deviation that is really acceptable. So it means that the method that we are proposing is robust and can be used in different labs. So the final USP proposal that we have submitted, then it's using dissolving the sample in 25 microliters of the sample in 3 milliliters of CPME. The reference standard from USP are prepared the same way. We have simplified also for the SST and proposed some reference standard from the USP instead of the corn or the olive oil. The method is done on an HPTLC plate RP18 with the fluorescent indicator. The developing solvent is really simple. It's acetonitrile CPME 7.3. There is a saturation and there is no activation. Then the application volume is 8 microliters. Derivatization is using the modified anisaldehyde sulfuric acid reagent. And for the detection, we have the long wave UV and the white light R and the white light T after derivatization. When you look at the fingerprints, so here it's what we obtain with all the USP reference. So you see that here the method is really colorful, and each oil has really a different fingerprint. So it can be some additional zone or missing zone, or it can be some intensity difference between each oil. In white light, in the detection C, you have also some color information. Some are more pink, some are more violet. So the method is now proposed and submitted, so it will be published for comment, I think, soon. What we have done after that is test also some sample from the market. So we have collected many samples from our lab and other employees here. So you have here the fingerprints of the olive oil. So you see that all the fingerprints are similar. They have some the same sequence of zone, but they have some difference of intensity, but it's still accepted in the natural variability of the oil. Same result for the rapeseed oil. So you see that here all the fingerprints are similar. We have done the same with some sesame oils or with sunflower oils. So you see that with the sunflower oils, we have a bit more of difference, but it's still accepted as the sunflower oil. The next step, when we submit this project to the USP, then we were contacted by the industry because they wanted to use this method. But for that, we need to transfer this method to the industry. So it means that it needs to be a simple method, fast one. So the developing time should be around 15 minutes maximum. Use more green solvent and be able to detect adulteration or mixture. And this method has to be easily transferable. So what we have done is we went back to the USP proposal and look where we could do some change to reduce the time. So the first thing is the standard solution. Here, we don't need to have all the USP reference standard because the goal is to apply the reference from the industry and compare it to new sample. So on the same plate, you will have one reference and one sample. Then developing distance was set at 70 millimeter from the lower edge. Here we will see if we can reduce that or if when we reduce, we are losing also some resolution. So we will look at this. Then we wanted to know if the 20 minutes of saturation are really needed or not. And the application volume also to reduce, same as the length of the band. So here we are using 8 microliters for 8 millimeter bands. Then for the derivatization step, so for the USP, we propose to use the modified anisaldehyde sulfuric acid reagent, which is using a heating step at 100 degrees for 6 minutes. So here it's also somewhere we could reduce the time. So the first step is the developing distance. So here I told you we start with 70 millimeter. So we have done the same plate, but with 60 millimeters. And then we look at the difference. So from the developing time, we are gaining 2 minutes difference. But when you look at the resolution between the peaks, we see that we have less resolution. So this is also something that we don't want to have, because if we need to discriminate oil or detect some adulteration, we have to be sure that the zones are well separated. So here we stay with 70 millimeter. Then we look at the saturation. So in the initial method, we use saturation of 20 minutes to be sure that it's really reproducible. And here we try without the 20 minutes of saturation. You see that the RF value are higher, which is normal, but also the resolution between the peaks are really better. So in that case, because the industry wanted to have on the same place the reference and the sample, for the reproducibility is not the main criteria. So that's why here at the end we have selected without saturation, because it's giving us better result, and actually it was quite reproducible without the saturation too. Then for the derivatization step, so we wanted to see if by using the regular anisaldehyde sulfuric reagent, we could detect the same thing as the modified anis. So we look at some specific oil. Here is the corn oil. And you see that with the corn oil, there is one zone that is highlighted with the orange arrow here. This zone has to be present in the corn oil. So here we see that we can detect it with the regular, but also with the modified one. So the regular anisaldehyde reagent is using a heating step at 100 degrees for 3 minutes. So instead of 6 minutes for the modified one, so that's why we have decided to keep the regular anisaldehyde sulfuric acid reagent. At the end of the transfer to the industry, we have a comparison. We did a comparison of the developing time. So here, because we keep the same mobile phase, we keep the same developing distance, so we have the same time. So it's 9 minutes 30. Then with the new method for the industry, we are not doing the saturation step. So it means that we are gaining 20 minutes. The humidity control was anyway not done. And for the derivatization step, the proposal for the USP was 6 minutes of heating after derivatization. Here, with the last proposal for the industry, we have 3 minutes of heating after derivatization. So at the end, instead of having a method that was doing 30 minutes for the USP, we have now an analysis time of 12 minutes. So we really reduce the time and we enter the criteria from the industry. Same thing for the solvent. Initially, we had 50 milliliters of solvent to develop one plate. So one plate means that you are developing 14 samples, for example. And here, with the transfer of the method for the industry, we are using only 15 milliliters of solvent. So we are really saving solvent and time, and that's why the method was then successfully transferred into the industry. So Paul will now explain you how they did that in their industry.
So thank you, Tin, for the detail on the development of the method. So now we will move to the applicability and the needs that we have to check, including the natural viability of the oil to have really an application in a factory. So the need was to have a fast and robust answer for each matrix. And this requires the validation of the method to set up acceptance criteria to be able to differentiate from a valid batch to an adulterated one. So to have a yes-no answer without any place for interpretation. So first, we have to identify the specific markers for each adulterant that will change the fingerprint of our oils. And it's critical to investigate the natural viability of the different oils as it will impact the fingerprint. Then, of course, we have to check the reproducibility of the method to have robust data. So we did the exercise on 3 different oils. So the palm oil that you see there, the rapeseed oil there, and the sunflower oil. So we have 22, 20, and 17 batches for each oil, and we repeat it in triplicates. So with that, we have enough data to set up acceptance criteria. So just for clarity, we will focus on one specific example, so the sunflower oil. So here it's the peak height for the specific markers of adulteration we spot. So we have here the sunflower peak height distribution, and on the below we have each retarded front where we check the variability of the peak height. And here we have the peak height on the left. So here is the distribution for each one, and more details about the one at 0.38. So we have the peak height here. So as you can see, we have the replicate 1, 2, and 3. And here it's batch to batch peak height. So with that, we were able to calculate a total standard deviation, combining batch to batch variability and replicate to replicate variability. So this we can fix an acceptance criteria for a maximum and a minimum one. So in our case, we only use maximum acceptance criteria. So when these acceptance criteria are fixed for all the specific retarded front where we can detect the specific marker, we can do the detection performance of the method. So here, what we did, so we adulterate the sunflower oil with different other oil up to 5, 10, and 25% of adulteration that will come from the added oil. So here we use cotton, safflower, corn, sesame, and soy oil. So here, first example, so for the sunflower oil adulterated with cotton oil, we compare both of the pure fingerprint and we check the markers that I specified you before. So we have two, one at 0.43 and one at 0.38. So then we can see the increasing of the peak in the fingerprints in the sunflower adulterated with cotton. We did the same exercise with all the different adulterants. So for safflower, the zone is the same. For corn, the zone is at 0.32. For sesame, it's at this zone, and for soy, it's also at 32 and 0.38. So the detection of adulterant was possible thanks to the deviation of the sunflower fingerprint profiling. So we know if there is an adulteration by detecting at specific retarded front value that will come from foreign oil. So for the detection capability, after that, we enter the peak height measured for adulterated sample that we also did in triplicates in the acceptance criteria calculated before. So here, one example for the retarded front at 0.32, we have our acceptance criteria here, and in blue, it's the pure sunflower oil batch peak height. And after here in the circle, so the point, we have here in green the pure one, that is a mix of all the sunflower oil batch that we test and inject in the system. And then we have 5%, 10%, 25%, and the pure corn oil here for the peak height at this retarded front. So we did the same for soy, cotton, safflower, everything at all the different markers that we detect before. And we can check so easily. We can see that cotton is really well detected at 5%. But then, for example, with sesame, it's a bit less sensitive for the detection of adulteration because 25% is below the maximum of acceptance criteria we set. So to summarize, here what we've got with different oils. So here's the three oils we use, so sunflower, rapeseed, and palm oil. And here's the detection capability we have in terms of percentage of adulteration with cotton, corn, safflower, sesame, soy, and palm kernel oil. So for most of the adulterant in sunflower, we can reach 5% of detection, but then we have also some oils where we are less performant, for example, with sesame, or for example, in rapeseed, where cotton, corn, and sesame oil are less well detected. So this came from the a more close fingerprint between the rapeseed and the adulterant oil. So this makes the adulteration detection more difficult. So for more details, it's available in the publication that we did with CAMAG in food analytical methods that was published this year. So to conclude, initially, the method was not for industry purpose, but this method was successfully adapted for the need of a fast routine analysis. We confirm the performance of the method with a statistical analysis, highlighting the validity of HPTLC as a quality assessment tool. We have at the end a rapid and reliable method for oil adulteration detection, and it was successfully optimized for routine analysis, and it's a ready method to transfer. Then we have just some drawbacks for factory implementation, that is the use of organic solvent. So this requires a specific setup in terms of safety for the use of this method. And then, so the HPTLC is also a versatile, it's a versatile device. So therefore, other method could be developed for quality control. So really to the end, that makes HPTLC a high valuable and feasible tools for adulteration and authenticity evaluation. Thank you for attending this seminar, and thank you for your attention. And if you have any question, don't hesitate.
Thank you to our speakers for that interesting presentation. So we'll now move on to the last part of today's webinar, which is the question and answer session. So the first question here that we have got is, how do you improve the separation of closed peaks?
I can answer this question.
You have seen that we did some tests also without saturation, and without saturation, we succeed to improve the resolution. So this can be one direction where you can go if you want to increase some separation.
That's great, thank you. This next one here is, what is the modification for the AS modified? And in brackets here, concentration or other.
Yeah, actually, it's the concentration of the ingredients that are inside the anisaldehyde sulfuric acid, and also the heating step. It's longer with the modified one, so like this we have difference of color too. So this recipe will be inside one application note that we will produce soon related to this case study.
That's great, thank you, Tian. So this next one here is, how is the industry easily detecting increases in intensity?
So following this study, what we have done at CAMAG is that we have implemented in our software one impurity tools where you can set acceptance criteria, like Paul has explained during the webinar, and you can select the specific marker, so the RF value, and set the acceptance criteria, and the software will check at this area and tell you if the signal is increasing, and like this, if it's outside of your acceptance criteria.
That's perfect, thank you. This question is, we see that Nestlé is considering the natural variability of the oil by calculating the acceptance criteria for each peak. Is this something CAMAG is willing to integrate into their software?
So it's for me again. Yes, we are thinking about this to integrate a tool to create a reference pool that it's accepted by the industry, and then to calculate how you have all these acceptance criteria that Paul has described during his presentation. So it's something we are working on it, and we are discussing that right now.
Perfect, thank you. And we've got time for one more question, and this is, are the peak heights coming from scanning densitometry or from profiles generated from images?
So yeah, I will take this one. So the peaks are coming from the profile generated from the image. So we don't have to do the scan step.
That's great, thank you. Well, that's all we've got time for today. So thank you to our speakers for today's discussion, and thank you to everyone joining us online. Please feel free to send over any further questions offline, and we'll follow up with these after the event. And to do that, all you have to do is email me at editor@selectscience.net. If you're interested in receiving a certificate of attendance, this will be shared with everyone who has attended live today via email a few days after the event. And if you would like to listen again to today's webinar or invite a friend to listen, it will be available to watch on demand in just a few days' time. Goodbye, and thank you once again for joining us.
Thank you.
Thank you.
Thank you.